Hello. In this topic, we'll be delving deeper into trigonometry and particularly looking at sort of the values of sine x, cos x, tan x, and it's all stuff to do with these three trig functions. Okay. What we're going to look at in this section then, to start off with. Again, like I said, we're going to consider obtaining all possible different angles for sine, cos, and tan. So, for example, how we could get sine of 220, cos of minus 90, and so on, right? Slightly more different angles that we're used to. Um, okay, so how are we going to start this off then? Well, what I'm going to do is draw a particular circle, right? Now this circle, if I draw it from the center, uh, a slightly better one than that. There we are, very rough circle, but this circle in particular has a radius of 1, right? So it's going to be 1 there, it's going to be 1 there, minus 1 down here, and minus 1 here, on the xy axis, right? Right, and so we call this a unit circle. Okay, so I'll mention a unit circle is a circle with radius 1. Okay, if you see that mentioned anywhere, unit circle is a circle with radius 1. You might see other shapes like a unit square, which basically means the sides are all 1. Okay, anything to do with unit, something is like 1 basically. It's like the standard sort of measurement, right? Hence a unit. So unit circle radius 1. Well, why am I drawing this then? Well, let us consider any general point on the circle, right? P. And P has the point xy, a general point xy. Now, this is a circle on the centre with radius 1. So we know that this will have the equation x squared and y squared is equal to 1, right? Okay. Well, then what if I then consider from the centre at 0, the origin, what if I draw the line connecting to the point, right? Oh, there, right? Well, and then actually, if I then do the vertical and horizontal to it to make a triangle, well, this would be x and that would be y up there. So we have this sort of triangle here, right? So that's the point P up there. With the x coordinate there. So we go x along and then y up. And then we have a right angle there. So that's what I've done, right? So I've just drawn a generic point on the triangle, and then I did x across and then y up, right? Because the general point is xy on the triangle there. Okay, now again, the radius is 1, and obviously it has to equal 1. Now, if the radius is 1 and we start from the origin, well, this length here from O to P is the radius, right? That would then be 1, right? So I have this triangle here. Okay. And then, well, this would also create an angle theta, right? Between the x-axis and our point, right? Which should be there. Okay. Now we can use a bit of SOHCAHTOA from GCSE, and actually we can kind of express x and y in terms of sine and cos, right? So we'll get rid of this now. Well, firstly, x is also the adjacent to the angle, and y is the opposite or facing the angle, right? And obviously 1 here is the hypotenuse. And so actually, if we then use SOHCAHTOA, we can say that firstly, that sine of theta is going to be opposite over adjacent, right? So opposite over adjacent. Hypotenuse, sorry, hypotenuse. And the opposite then is this y over the hypotenuse, which is that's actually just 1. Well, therefore, we're just dividing y by 1, that's just y. Therefore, we can deduce that actually y is just sine theta. So it's sine of the angle the point makes with the axis, right? And like similarly, then we can also say that that x, well, we can do cos, right? So the cos of the angle is going to be now the adjacent over the hypotenuse. And then the adjacent here is x, and the hypotenuse is again 1, right? And therefore then, that's for saying x is equal to cos theta. Right, okay, well then actually we could actually specify more clearly then that pxy, if I redraw the triangle then, the circle, right? So we have the circle with radius 1 again, and then the point P up here. Now P, we can say xy, but because x and y are cos and sine theta, respectively, we can say that x is now, the x coordinate is now just cos theta, and the y is just sine theta. Right, and so we can say it's cos theta along there, and sine theta up vertically up there, okay? And so actually then, with this unit circle, we can express any point on the circle by just the angle it makes with the axis, so the x-axis, right? So for example, say if we had another point Q here, then the angle it makes there, let's say that's alpha, and then this would be cos alpha along the x-axis, and sine theta, or alpha, down, vertically down. And so we have this same position where the y coordinate is the sine, and the x coordinate is the cos, right? And so again, Q would then be cos alpha, where alpha's just another angle, right? I don't want to reuse theta again because they are different angles because they're different points. Cos alpha, sine alpha there. And so basically, yes, so hopefully that shows that actually for any point on this circle, unit circle, we can just give the xy coordinate as just cos theta, sine theta for some angle theta it makes with the axis, okay? And so why is this useful then? Why are we doing this? Well, we can work out then various values for cos, sine and tan theta for various angles. By considering the angles again, we make the axis like this. So we're going to look at some questions then. Okay, so example 1 then. Firstly, we need to find the value of sine 90. Now, obviously, with all these questions, obviously the obvious question people will think, well, just put that in the calculator. I've not seen questions, like this obviously in an exam, because again, you have a calculator. But I do want to go over this sort of unit circle because the specification here says you need to know how to use the unit circle by setting x to cos theta, y to sine theta there, okay? So we're going to look at approaching these questions by this sort of way, rather than just the calculator. Anyway, so firstly we have sine 90. Now, so what we're going to do then is, again, we draw our axis, x and y. Now, sine 90, so we want 90 degrees. We're always going to measure our angle counterclockwise from the positive x-axis, right? So from the positive x part, right? And then we go from there counterclockwise, right? And then if we go the full way, that'd be 360 degrees, right? And then if we return back to where we started there, right? If, say, we wanted 45 degrees, well, it'd be halfway there. That'd be 45. And say if we wanted 180 degrees, Well, if we start from again the positive x-axis part, well, firstly, we would have to go 90 degrees to that y-axis part, and then another 90 degrees, we got 180, right? So if we wanted an angle of 180 degrees, we start from here and we end there. And so we end up there, right? If, say, we wanted 145 degrees, we firstly have 90 there, but then we would have to go some way in the middle here. So 145 take away 90 would be 55. So we need to go another 55 degrees in this region there. And so then if we add 90 and 55, we get 145, right? So that would be my angle in that case. And we can also go backwards as well. So we might have negative angles like this, which I imagine some people are like, how does that make sense, a negative angle? Well, the negative angle is when we go the opposite direction. So obviously we measure all angles starting from, again, some here on the positive x part, and we go counterclockwise until we get to 360 degrees. But if we go the other way instead, clockwise, then that would be the sort of the negative direction. So say if we had minus 30 degrees, well, it'd be 30 degrees, but we're going to go that way. So it'd be from the same axis there, right? 30 degrees there. If we wanted, say, minus 120, well, firstly we'd have to go 90 the other way, and then we'd have another 30 degrees, right? So that'll be 30. And this will be 90. So overall, again, we get 120. And it's negative because we're going the sort of the negative direction, right? The opposite way. And so we can actually express an angle in both the positive and the negative direction, right? So let's take this negative 30 again. So angle 30 clockwise from the positive x-axis there. We can also go the other way around, right? And eventually we will reach that angle there, right? And so that angle, well, the whole turn is 360. So the whole angle here is 330, right? So we could say that equivalently that negative 30 degrees is sort of the same as 330 degrees, right? But yeah. So we can get the same angle by positive and the negative side, okay? Right, okay, so let's have a look at this question then. So 90 degrees. So now that we know how to, find angles using this sort of diagram. Well, side of 90, well, firstly we're going to consider the 90-degree angle. So it's positive 90. So we're going to go, 90 degrees that way. Well, that would just be a right angle then, wouldn't it? Towards the axis there. So then, we end up here, right? So if we have then, remember our unit circle, 90 degrees, if we're moving 90 degrees from the x-axis, it's going to end up there, isn't it? Our point P is now going to be on the y-axis, wouldn't it? Because if we turn 90, we start here, and then we end up there, right? And so it has a length of 1, the radius. So what we've got essentially is we have a point here, and it's 1 upwards, right? Because the radius is 1. So it's just there's no horizontal component. There's no x, right? There's no x. So that means that x is equal to 0, and then y would equal 1 then, right? If it's just straight up by 1. So that means our point is 0, 1. But we also know x and y, if we go back to what we discussed, x and y can also be expressed as cos theta and sin theta with the angle we turned. So in this case, 90. So therefore, if x is cos theta, then we can say that cos of 90, which is the angle we've got, right? That's going to be equal to 0. But also, the sine of 90 will be equal to 1. And there we are. So that's the value we get. Sine of 90 equals 1. And you can confirm that by the sine graph. So remember the sine graph looks like this. Well, at 90 here, it's indeed 1. Right, remember we looked at that in the last chapter at GCSE as well. So that confirms what we know. Okay, so sine of 90 gets us 1 because it's the y coordinate, right? And the y value has to be 1 if it's a radius of 1 there. Right, okay, and by the way, you can work all these out by the graph, but for the purposes of this particular video, we will be using this sort of a diagram instead to work the angles out. Anyway, so that's part A. Part B, then we need to work out sine of 180. So now 180 degrees in here. Well, we start again here, and we need to turn 180 that way. So this whole angle then is 180, and we end up on the negative x-axis, right? Well, again, it has to be on the circle, right? The circle of radius 1. That's the unit circle. So it has to be on here then, right? If we start in here and then we turn 180, it would end up there, right? Again then, that means in this case, if our point P is there, it's just a straight line, right? It's a horizontal line. So in this case, the length would again be 1, because that's sort of the radius, right? This will be 1 there. Well, there's no y coordinate, right? It's just horizontal. This is just the x part. So we can say that x is 1, and then y is, well, actually it'd be negative 1, right? If it's negative 1, because it's on the negative x-axis. X is negative 1, and y would be 0, because think about it, there's no y component, it's just 0, right? Because we're not going up in any way. It'd be just going straight along. So it'd be 1 there. Well, it'd be minus 1 again because it's on the negative x-axis. So just finding the point then. So P would then be minus 1, 0, right? That's what that point would be there if we moved 180 from here. Okay, but again we know that x is cos, right? So we can say that cos of the angle 180 would then be minus 1. And then also y is sine of the angle. So we could say sine of 180 would get me 0. And there we are. So that's the value then. Sine of 180 therefore is 0. Right. Okay, part C, sorry. We need to then find sine 270. So if I, again, just draw a rough diagram, about 270, well, again, we're going to start here and move counterclockwise. And 270, well, that will be 90, then this will be 180. 270, we'd end up on here, right? We'd end up on the negative y-axis. So again, this point is going to be there. So it's going to be minus 1 along the y-axis because it's negative y, right? So therefore, our point here is going to be the x component is going to be 0 because it's on the y-axis, but y would then be minus 1, right? That's my point then. This point is 0 minus 1. Obviously the whole idea as well, remember the length also has to be 1, right? If you going from the center and then going to this point, it has to be 1, right? Because it's a radius, right? But there we are. Right, again then, y represents sine, right? So then we can say that sine of the angle, which was 270. I'll draw the angle there again. That's 270 degrees. Sine of 270 would indeed be minus 1. And again, that makes sense because the sine graph here, we can confirm this because 270 will be there, which indeed is at minus 1. Okay. There we are. Okay, then part D, we have cos 180. I'll write that up here. So again, the angle we're going to consider is 180. So again, if we move 180 along, starting from the positive x-axis, it would be on the negative x-axis. It would be there again. So again, if we're measuring from the center, right, the origin, it would have to be -1 there, right? Well, the x coordinate's -1, the y coordinate would be 0, right? So it'd be -1, 0, right? I'm just stating the coordinates at that point if the length is 1, okay? There we are. Right, again then, the x part is -1 and the y coordinate is 0, where again, remember that the x represents the cos. So that would mean that cos of the angle, which would be 180, would indeed get me -1. And there we are. So we've got the value then. Cos of 180 is -1. And again, you can check using the sine graph, the cos graph, sorry. It looks like this. Well, 180 is indeed down there, which is at -1. So again, we can check our answer there. Right, okay, part E, then we need cos of -90. Right, okay. So now this is a negative angle. So if we draw a little diagram again, right? So -90. So we're not going to go 90 that way, counterclockwise, anti-clockwise. We're going to move and turn that way instead. Right, we're going to go beneath the x-axis. So -90, we're going to go 90 this way. That would just be a right angle there, wouldn't it? So it would end up with a point, say there, right? And so that would be on the negative y-axis, and the length will always be 1. So that'd be -1 down here, right? So then the point then, well, x would be 0, and the y coordinates are -1 there, right? So again then, we've got the case when x is 0, y is -1. Well, x represents the cos. So that means cos of -90, which is that angle, would have to be 0 then, right? And there we are. So we can work out the negative part of the side, which is where we get the negative part, the cos or the trig graphs, right? So remember, the cos graph looks like this. We can also go on the negative angles as well. Well, this would be -90 there, which indeed is 0, right? Hence, there we are. So we can get negative angles as well, which doesn't make much sense, because you maybe like the terms of like triangles or shapes or whatever. It doesn't make sense to have like a negative angle. But in this sort of case, we can define it. We can get negative angles out of this if we just go the other direction to where we normally go, right? But there we are. Then part F, the last part of this, we need to find cos of 450. Okay. Right. Okay. So let's draw it here. So, well, 450. Well, we know that a full turn positively this way is 360, right? But that means then we go back to where we started, but we've technically turned 360. We did a full turn around like the whole axis, right? So we go back to where we are there. So hang on. Right? We go back to where we came from at 360. And then we need to do another 90 after that, right? And we end up again on the positive y-axis, because another 90, well, 360 that we did a full turn, and then we did another 90-degree turn, would be 450. So that'd be the angle there. So overall then, we just really moved 90 degrees from the start, because obviously one full turn gets us back to the start. So another 90 after that would indeed just get me on the positive y-axis, right? Therefore then, my point then, really, is just going to be 1 there. So our coordinate would be 0, 1. So x would be 0 if it's on the y-axis, and y would indeed be 1. Well, therefore, then x is 0, y is 1. Well, the cos part again is about the x, so that means cos of our angle 450 gets us 0. Okay, so again, we can do angles bigger than 360 by just doing a full turn and then going on from there, right? But yeah, okay. So let's have a look at this question then. So now it's talking about tan. Now we discussed how we can get sine and cos, but let's go back to our sort of diagram then. So we know a general point P if it's on a unit circle, so it has a radius of 1. Again, we know the angle is theta in general. And we know that we discussed that the x component would be cos of the theta because it's the adjacent. And the sine upwards, well, no, the y, well, it is sine, as that's the upwards or the y component, right? The y coordinate. And we can express it as xy as cos theta sine theta, as a recap that we did earlier. But we didn't consider what tan was in this triangle. So if I go back to this triangle then, well, this is sine theta, and that's cos theta, and this will be 1, because that represents the radius of our unit circle. And we get the point here, say. Well, the tan. Well, again, the tan of our angle is going to be the... well, this is the opposite, right? And this is the adjacent side, the cos. Well, remember SOHCAHTOA, tan is the opposite over adjacent. But actually, the opposite part is sine theta. And the adjacent part is cos theta. Or we could just say it's the x over y. No, what? Y over x, sorry. So if we find our y and x coordinate, we can say that tan theta is y over x, right? But if we can find the angle, then we can also find it that way. So and the point is that tan theta, we can also find in this way by just doing the y coordinate over the x coordinate, right? And we know how to find those two coordinates by considering the angles like we did in the other example. But anyway, so I'm going to highlight that then to make room. So we know that tan theta is the y coordinate of the x coordinate for any point P there. Okay, so let's put that into practice then with these questions. So firstly, we need to find the value of tan 45. So again, we're going to consider the 45 angle. So we're going to go 45 across here, and the angle then will be somewhere there, right? 45. So again, this will be the x coordinate, and that'll be the y part. And again, that'll be a radius of 1. The length, the hypotenuse will be 1. Now, so the tan of 45 then is going to be the y coordinate, which is the opposite, over the adjacent, which is the x coordinate. So our question is, how do we find the y and the x coordinate? Okay, well, this is where we need to be a bit algebraic, because, well, think about this triangle we have, right? We have 45 degrees, and this is 1, the hypotenuse. Now, if it's 45, and we have x and y here, if it's 45 degrees, that's in the middle of the quadrant, right? That's in the middle of this grid here. If it's in the middle, then we're kind of splitting it halfway, because this will be another 45 degree, and therefore we get 90 overall, which is the whole thing. Well, if we split it or bisecting it, or splitting it evenly in the middle, then actually that means that both x and the y coordinates have to be exactly the same. So therefore then, we can say that x equals y. So then we can find that because we can do Pythagoras theorem, because we know that the length is 1. So if we do Pythagoras theorem on this triangle, well, we would say that x squared and y squared would be 1. 1 squared, which is 1. But we also know y squared, or y is also x. So the x squared and then an x squared would be... so if we collect the like term, we can say that 2x squared is 1. And therefore x squared is a half. And then x is just root of a half, which we can say is root of a half. Which you can say it's 1 over root 2, which we can rationalise if we want to root 2 over 2. So that means both coordinates then are now root 2 over 2 for the x and the y part, because they both have to be the same if the angle's 45, if it's in the middle, right? Well, therefore then we can find tan, because now we know y over x. Tan 45 is y over x. Well, y is root 2 over 2 and x is root 2 over 2. And they cancel because they're exactly the same, so we get 1. So therefore tan of 45, that value is indeed 1, right? So there we are. Okay, so part B then says we need to find tan of 135. Okay, so if we draw our angle again, so we're going to draw 135. Well, firstly we're going to go 90 that way, and then 45 more than 90, so there, over that gets me 135. So our angle's going to be over here somewhere, and we're going to start from here, and so that means my angle 135, okay? But also then that means if we then consider this angle here, we have an angle on the line, right? This 135 and this angle theta. Well, if I do 180 take away 135, this angle is actually 45. Well, we saw in the question we just did, with a 45 triangle and length 1, that the x and the y parts are root 2 over 2. Well, that has to be the same because we've got another 45-degree triangle. So this would be root 2 over 2 on the x-axis, but it would be negative because we're on the negative x-axis. Likewise, this y part up here would also be root 2 over 2. And so therefore then, that the x-coordinate's minus root 2 over 2, and the y-coordinate's positive root 2 over 2. So therefore then, tan of 135 is just y over x. So opposite over adjacent, which is just going to be root 2 over 2 divided by minus root 2 over 2, which should just be minus 1 because they cancel out again, right? And we're just left with negative. So there we are then. We can say that tan 135 gets me minus 1 there. Okay, so the idea is we can sort of use small angles that we know. For example, we looked at 45 in this earlier question to work out larger angles, right? By considering this idea of we could split into 2 different angles. But anyway, let's have a look at part C. We have tan of 225. So again, if we draw a little graph, well, firstly, tan of 225, well, 180 would again be this whole on this line here, we end up here. But then we need to move another 45 degrees there. And obviously then, that 45 degrees add the 180 gets me 225, okay? So overall then, we start here and end up there, that whole angle is 225, okay? Again, alternatively, as we discussed, this angle here was 45. So therefore, we can create another triangle, right? So we could say that, again, that's 180. And then another 45 would be there. So then we got the same sort of 45-degree triangle, right? So if I So again, the x-coordinate then would be root 2, there'd be root 2 over 2, but it'd be negative root 2 over 2 on the x-axis, on the x-coordinate there, because it's on the negative x-axis. And y would also be negative root 2 over 2, because now this point here, say, is on the negative x-axis, y-axis, right? Well, therefore, then, the tan of that, again, is going to be y over x, or the opposite over adjacent of the angle 45. So, tan of 225, then, our overall angle, is going to be negative root 2 over 2 over negative root 2 over 2, which should be negative 1 over negative 1, which should just be 1. So they cancel out again. So therefore, we get tan 225 is indeed 1. Okay. Cool. There we are. Okay, part D then. We now need to find tan of negative 45. Okay, so again, because it's negative now, we're going to go reverse to the direction. So we don't go that way, because we have negative 45. We'll be going clockwise instead, right, down here. So we're going to go 45 downwards, right, because it's negative. So it'd be like that. So again, then we can sort of construct a triangle where the x component, x over here, the x coordinate, going to be again root 2 over 2. That'd be positive because it's on the positive x-axis, but it'd be negative root 2 over 2 downwards on the y-axis, the y-coordinate, because it's on the negative y-axis, right? That's the y-coordinate is negative. Again, overall, then we could say that tan of minus 45 is again going to be y over x, which is going to be negative root 2 over 2 over positive root 2 over 2 for x. Should just get me negative 1. Therefore, we could say that tan of minus 45 gets me negative 1. Cool. Okay, then part E. Oh, I need more room. Okay. Yeah, I don't need to use my workings now. Let me make more room then if I rub this out. Okay, so part A then is tan of 180. So again, we're going to draw a little graph, and it'd be 180 degrees we need to go by. Well, if you turn in 180 degrees positively, it would end up there, right? That'd be 180 degrees. So again, we're going to end up here, right? Somewhere there. Well, overall, the length has to be 1. So that means the x coordinate's going to be negative 1. And there's going to be no y coordinate, right? Because it's on the x-axis. So we can therefore say that x is minus 1 and y would be 0 here. I'll do that. Hang on. I'll do that here. X would be minus 1, y would be 0, because that's my point, right? My point would be minus 1, 0 here. If you moved 180 degrees. So, that means then that if tan of the angle's y over x, we can therefore say that tan of the angle 180 is y over x, by y is 0 over x, which is minus 1, and that just goes to 0. So therefore then we can say that tan of 180 gets me 0. Okay. Cool, and then part F then, the last part, we need tan of 90. So again, we're going to draw a little graph. So we're going to move 90 degrees then. So it's just going to be a right angle, right? It's going to be there. Okay, that we move 90 degrees. from the x-axis. So again, it's going to be on the positive y-axis here somewhere. So it's going to be positive 1 for y. So the coordinate then is going to be x is 0, y is 1, right? So therefore we can say x is 0, y is 1. So therefore tan of the angle 90 gets me y over x, which should be 1 over 0. Well, hang on, we can't divide by 0. So therefore tan 90 we call is undefined. Okay, we cannot divide by 0. So therefore it's an undefined angle, which makes sense because if we go back to our, if I draw a very tiny tan graph, we have an asymptote at 90. We have an asymptote because the graph doesn't exist at 90. And we can see why now, because we'll be dividing by 0. That's why it's an asymptote. That's why it looks like the graph 1 over x, because we saw that graph, that reciprocal graph, right? Had a asymptote because it's undefined at 0. It's the same thing. Tan 90, we get this asymptote at 90 because we're divided by 0 in this way, right? But there we are. So that's some angles then. So hopefully you got a sort of gist now for how we can just create the angle by using this graph, utilizing the idea that it should always go to 1, which then we can find the missing angles for cos, tan, and sine. But okay, then this example then says find the sines. So basically, is it positive or negative, right? Of sine theta, cos theta, and tan theta in the second quadrant. Now, I'll talk very, very quickly about these quadrants. I did talk about it, but I'll explain it, now, right? So we have a point of reference. So in the XY grid, it's split into 4 spaces, hopefully you can see, which we call quadrants. This is the first one that I've highlighted. We call that the first quadrant. And in this quadrant, that's when both x and the y's are positive, right? Because on the positive and y-axis, right? That's the space that occupies. And then we move 90 degrees. So we move to this one, which is now what we call the second quadrant. Right? Now, this is obviously going to be when x is negative, but y is positive. And then we move to the next part, which should be down here, which is quadrant 3. And this is where both x and y are negative, because they're both on the negative axis in this space, for any points in this space. And then lastly, we have this last quadrant, which should be the fourth one, right? And that's when x is positive and y is negative, okay? And so we split this up into 4 different quadrants, okay? And so, yeah, these are what we label these 4 spaces in the XY grid, okay? Now, it's saying in this question, find the sine in the second quadrant. So what we're going to do then is, we're going to consider an angle, again, a generic angle in this sort of circle, in this space here, the second quadrant. So if I draw a typical triangle, then, make it somewhat neat. There we are, so an angle theta, which is in the second quadrant. Well, again, you can call it 1 if you want to, but we need to, doesn't really matter in this case, because we know that the x part down here is the adjacent. That's gonna get me cos. So cos of theta, with the length of 1 again, because it's the unit circle. By the way, we are in a circle, I should mention, but there we are, and obviously the point is on the edge. But I'm not going to draw the circle out every time, okay? The whole idea is that we have a length of 1, right? That's the whole idea, essentially, when we're in a unit circle. So if we have a hypotenuse of 1 and an angle theta, this gets me cos theta on the negative, on the x part, and the y part up here would get me the sine theta, because it's opposite the angle. Now, talking about the sines then, well, this cos theta is on the, it's x, right? Again, we saw that x is cos theta and y sine theta. Hopefully you can see that, right? That's the x point, which is the cos theta, and the sine theta is the y part. Well, x is negative here, isn't it? Because it's on the negative x-axis. So x is negative. Well, that means that cos theta is negative because it's just the x part. Right? And also y would be positive because it's on the positive y-axis, right? If we then extended it, it's on the positive y part, right? That coordinate, right? When we extend this line to, that point here has a y point and the next point, right? So that'd be, there we are. Well, again, the y part then is positive because it's on the positive y-axis. So therefore, y is sine theta. So we can say that sine theta would also be positive in the second quadrant. But then it's talking about tan. But we also know that tan is y over x, or the opposite over adjacent of our triangle. Okay, but we discussed that y is positive and x is negative. So what we are doing then is dividing a positive number y by a negative number x, right? Well, therefore then, if you divide positive by negative, plus over negative, well, that will get you a negative, right? So therefore, tan of theta would also be negative in the second quadrant, right? If we draw an angle in the second quadrant, there. Okay, so there we are then. And again, we can then confirm all this, right, by if we consider their graphs. So firstly, the cos graph, right? Just a very quick sketch. So if it's on the second quadrant, that means the angle then has to be between 90 and 180, because obviously that would go 90 there, and then the overall would be 180, so it has to be in between, right? This angle, this overall angle there, right, would be 90 and then some, right? Well, if 90 is there and 180 is there, we can see that the curve between 90 and 180 is underneath, so it's on the negative y-axis, meaning it's negative. Hence, there we are. If we did the same for the sine then, so if it's in the second quadrant, the angle would be between 90 and 180. So the sine graph looks like this. So again, 90 is there and 180 is there at 0. Or again, between here and here, these 2 points, it's positive. It's on the positive y-axis, so it's positive. And then lastly for tan, if we draw the tan graph, there we are. Well, 90 is obviously the asymptote, and 180 is where it returns back to 0. So it's going to be down here then, right? Between 90 and 180, it's on the negative y-axis, so the tan is negative. So there we are. So we can prove all our results by considering the graphs as well. We can do the same then for the... so if I draw another graph, we can do the same for the other quadrants as well. So as we discussed here, if our angle is in the second quadrant, so there we are, then we get positive sine only. So I'm going to say sine there for positive. So I'm just going to label only the positive values, right? If we then worked in the first quadrant here, so we made an angle theta to the x-axis, as we always do. By the way, every angle we make with triangles should be made by the x-axis only. So there we are, for example, as well. But anyway, so in this case, well, x is positive and y is positive. Well, x represents cos and y represents sine, remember? So both cos and sine are positive, right? So we could say cos and sine But also tan would be positive as well because it's y over x. So what? So it would be the well, y and x are both positive coordinates, right? Again, if we draw a graph there, so the x and the y coordinates are positive. It's in the first quadrant. So that means tan. If you divide into positives, it would also be positive. So you can also add tan to this as well. So all three trig functions are positive in this quadrant. If the angle's in the quadrant. If the angle is now in the third quadrant, so we have to go that way along. So we have an angle between 180 and 270 now. So again, if we call the angle between the x-axis here, well, here then, the x is negative there, and the y is negative as well. So that means if sine and cos represent y and x, they're both negative. So x and y are both negative. So that means sine and cos are both negative here. But tan would be positive because remember tan is divided y over x, the y and x coordinates. Well, because y and x are both negative here, because again, just simple fact that we're along the negative y-axis there and the negative x-axis there, we're divided two negatives, right? So we'd get a positive out of that. So only tan, if we evaluate an angle, say like tan 220, that would be positive, okay? But if we did sine of 220, it would be negative. It would give me a negative answer. So only tan is positive there if we put it at an angle between 180 and 270. Then lastly, we've got the last quadrant here. So again, if we make an angle to the x-axis here. So again, if we draw a line there, well, the x coordinate here is going to be positive, but the y will be down here will be negative, right? There, right? So it'd have negative y and positive x. So x represents cos. So that means if x is positive, then cos would be positive. So you can say cos, but sine would be negative because it's y, right? Y sine theta with this triangle. And y is negative here, as we see it's on the negative y-axis, so sine would be negative, and also tan would be negative because y over x, we divide them a negative by positive, that would still be negative. So only cos, if we evaluate it at an angle between 270 and 360, which again, if we go all the way around somewhere there, there we are. So we only get cos positive in this case. Okay, so why are we doing all this then? Well, we'll look at some examples in a minute, but it's helpful to break down larger angles, so angles above 90, into because we can create similar triangles with angles that are just between 0 and 90. So we can work with smaller angles that we know. We'll look at some examples in a sec. But if I then just simplify this then, cos, sine and tan, I'm just going to call it all trig functions are positive, right? So all three trig functions are positive. So the positive in the angles in the quadrant. So remember the first quadrant is between 0 and 90. The second quadrant here is between 90 and 180. The third quadrant down here is between 180 and 270, and the last quadrant is between 270 and 360. So if we evaluate any angle, what this is basically saying again is if we have a particular angle, say for example tan of 135, that's between 90 and 180. If we look here, only side is positive between those angles, so tan would get me a negative result here. Obviously I don't know what the result is per se, but it'd be negative something, right? But anyway, so what there's a special type of name for this. If we start with the first letter of everything, we get something called a cast diagram. So obviously C represents cos here. Then we move upwards to all three trig functions A. Then we get sine, which would be the S, and then T for tan, which is where it's positive there. So if we start from cos and work our way around the grid, that gives us the ordering of the trig functions that are positive, right, in the quadrants, okay? So we call that a cast diagram, which we will see thrown around, like the textbook or wherever else you look at your maths. But yeah, so the cast diagram tells us the angles for which certain trig functions outputs of it positive, essentially. And yeah, so there we are. So again, why is all this? Why bother? Well, I did mention it allows us to then consider acute or smaller angles just between 0 and 90. So we're going to look at some examples of this in question because I think it's harder to explain it before without seeing anything, yeah, a particular example. Okay, so we're told here to express in terms of trig ratios, which means, by the way, in terms of sine, cos, or tan, of acute angles. So these are going to be between 90. Okay. So firstly, sine of minus 100. Well, again, we're going to do the same thing that we always did. And just consider the angle minus 100. So that would mean, because it's negative, obviously, negative angle, we're going to go clockwise, going that way. But obviously that would be 90 there, but we'd need another 10, right? So we need another 10 after the 90 to get overall 100. Now, we could also then consider this angle here, couldn't we, between the x-axis there. And that is a strategy, by the way, of these questions. You should always be aiming to make an angle from the x-axis, like here, okay? So this angle then, overall again, each quadrant has to add up to 90, right? So if we get 10 from here, well, this means this angle is going to be 80 then, right? To get me 90 overall from this quadrant. So if I then get rid of this now, this 10, I then got this triangle here, right? And so now we split up this weird angle of a minus 100 into just 80, which is acute. So now we can express it in terms of 80. This is where the cast diagram comes in, right? So again, we can say that angle is minus 100 degrees. But equivalently, we've got this triangle of 80 between the x-axis. Now, this is where the cast diagram, so I'm going to label it C-A-S-T here. This is where it's going to come into use, because sine of minus 100, we can also express it in terms of the angle 80 here, okay? So that's what it's talking about, expressed in terms of acute angles. So it's going to be sine of 80, okay? Because we can get the other value of for sine here. But it's not just going to be equal to sine of 180. We need to consider if it's going to be plus or minus, right? And I'll show you the sine graph after this to really make it make sense. But this is where the cast diagram comes into use, because the cast diagram tells me whether my angle should be positive. Well, the sine of it will always of the angle gets me a positive or negative result. So minus 100, obviously we end up in the third quadrant, right? That's where we are drawn to, right? Here. So we ended up in the third quadrant. If we rotated minus 100, that's where we end up. Well, this is marked tan, right? T for tan. If we label, C-A-S-T in this order, that tells me what is positive. Now, because we have T here, that means only T is positive, so tan. That means sine and cos, the other trig functions, are negative, meaning that sine of minus 100 is equivalent to 80, but it be negative, okay? Because it cannot be positive because of the cast, right? Only tan is positive at this angle here. So we have to whack on a negative, right? But if we can find sine 80, then we just whack a negative, and then we get this other result for sine minus 100 there, okay? So this is what I mean by the idea we can break down larger, more weirder, complicated angles into smaller ones in this case by using this cast diagram, okay? Now we can confirm this by looking at the sine graph to make it make sense. So we have, let's draw a sine graph then. There we are. So sine 80, well 80 is going to be like there, right? And minus 100, well this is going to be minus 90, so minus 100 is going to be a bit off to the side of it there, right? So hopefully you can kind of see the symmetry, right? So again, at the top of the hump it's going to be 90, so this will be 80 there. And then again, at the top of the hump down here, it'd be negative 90. So then this would be negative 100. Well, hopefully you notice again, like the gaps between 80 and 90 there, and minus 100 and minus 90 are the same. Well, yes, they're the same. But one's on the positive y part and one's on the negative y part. Well, they're just saying that sine of 80 then has to be the negative to sine of minus 100 degrees, which is where we get this from. Okay, so the graph, hopefully you can see, reinforces why sine of minus 100 is the negative of sine 80, because the angles are you know, minus 100 is below the y-axis. No, sorry, below the curve, below, and 80 is above, so it's on the positive y part. So they're just negatives of each other. But there, yeah. So there we are. So okay, cool. So we expressed it in terms of acute angles, okay? So that's what we mean here. Okay, let's have a look at part B then. We have cos of 330. So let's draw another diagram. So 330, well, it's positive 330, so it's going to be up around here. And that'd be 270 here, but then we need to go another 60 along, because 270 add 60 is 330. So it would end up somewhere there, right? So we'd have an angle there of 60. If we go along and get 270 there. So then 270 at 60 degrees there will get me 330. But then, if we then consider this angle here, that would be 30, right? Because I'm just 30 away from a full 360. Well, there we are then. So we can also then equivalently, right? If this whole angle is 330, we get the equivalent angle 30 with this triangle here, right? Well, then that means then we can say that cos of 330 is equivalent to cos of 30, but we need to consider if it's plus or minus this, okay? And this is where the cast part of it will come into play. So we'll label it CAST in this way. Well, in this fourth quadrant here, so we notice it's C. So cos is positive, right? So the cosine of an angle is positive, right? The cos is positive at this point. So that means then, indeed, it's just going to be plus 30, because cos of 330 will also be positive. So there we are. So we can equivalently express cos 330 as cos of just 30, okay? In this case there. And it pretty much works the same way with all other types of angles. I mean, we'll look at tan 500 up here. But that's the whole idea, right? We can consider a larger angle and then create a triangle of the smaller angle or the acute angle. And they're effectively the same. We just need to consider, is it just going to be plus or minus each other? Okay, and this is where the cast part comes into play. Okay, so tan 500 then for this last part. So again, we're going to consider drawing a little graph to show the angles. So 500 then, well, 360 again is going to be a full turn. We end up back here, right after 360. Well, 360 to get to 500, we need another 140. So we're going to get 90 there. And so then to get 360 to 500 is 140 left. So we've got 90, so we need another 50. Okay, so 50 there. So if we draw a triangle, we have an angle 50 there. So overall then, if we turned 360 degrees, and then we turned another 90, which would be 450, then we turned another 50 there, we get 500, okay? So that is the position or the angle we're working with, 50. But if that is 50, then the angle here between the x-axis, so again, always consider the angle between the x-axis, would then be 40, right? Because then again, overall has to be 50 and 40 gets me 90, okay? So then if we just get rid of this, we can say that therefore then, the overall angle of 500, the tan of 500, has to be sort of equivalent to tan 40, but it will either be plus or minus. Well, which sign exactly? So to work out the sign of tan 500, we need to consider the cast diagram again. So just labelling all the quadrants, C-A-S-T, in this way. So we're working in this quadrant again, that's where our angle's at. So only sine is positive here. So that means tan is negative. So that means it needs tan 500 is negative tan 40. So it's equivalent to this angle 40, but then we need to consider if it's plus or minus, okay? And so yeah, there we are. So once you get the hang of it, hopefully it's not too much work, it's not too hard. But we can break down and gather further angles in this way by considering just, you know, smaller angles, right? Acute angles between 0 and 90. So again, we broke down tan of 500 into just an angle of 40. We can do that by this cast diagram, okay? So because the cast diagram tells us if it's going to be plus or minus, right? What sign is tan of 500, okay? And so once we could do that, then we now have the tools to basically gather equivalent angles or equivalent expressions for larger angles, right? This will be very helpful for when we solve certain equations later on in the chapter, where we need to find larger angles, but they're also the same as the smaller angles as well, okay, or plus or minus of it. Which will help us solve it. Because if we can find tan 40, then we can find tan 500, and then we can find other angles as well in this similar sort of way. So that's the whole idea, right? We can work with smaller angles, and then we can use this idea to work out equivalent larger angles, okay? But yeah, okay. So that's really it, really. In relation to this sort of method of considering angles on the quadrant. But yeah, so that's the main idea then. The main idea is that firstly, a unit circle is a circle from the origin at with radius of 1. And so therefore then, we can consider any general point at an angle, theta, if the hypotenuse is 1, the y and the x part, well, y would be sine theta because that's opposite the angle, and x would be cos theta, and so therefore we can find angles of sine, cos, and tan in this way. And obviously the cast diagram that we looked at as well tells us the sign of either cos, tan, or sine. Okay, we're going to leave off with this last question then, and this will be useful later on, but for now we need to prove for all values of theta, firstly, sine squared theta add cos squared theta is identical to 1. Right, so again we're going to consider this sort of our graph we're working with. Now again, let's go back to our unit circle, right, with radius of 1. So if we take any general point on the unit circle, right, so that means for any angle, right, doesn't matter what angle, what point it is, it will have a radius of 1. And so therefore then, as we discussed, the if we then construct the triangle from this, that's the angle theta, and we have point P there, and length hypotenuse of 1. We discussed this for sine theta because it's opposite, right? Remember SOHCAHTOA, and then cos would be down here. Well, this represents x, right? And this sine represents y. Now, we know that by Pythagoras' theorem, that the hypotenuse and the opposite and adjacent squared, so x squared and y squared would then equal the hypotenuse squared, which is 1 squared, which is 1. But we know x and y are cos and sine. So we can say that x squared is going to be cos squared theta, and y squared is going to be sine squared theta. And that's going to be equal to 1. Well, it's going to be identical to 1, actually, because it will be true for all values of theta. Because, again, it doesn't matter where I put my point on the unit circle. It could be here. There's still an angle theta, and it works in the exact same way. Okay. But anyway, there we are. Cool. There we are. So there we are. So we proved this identity here, right? Okay, part B then says we then need to show that tan theta is sine theta over cos theta. So again, if we go back to this triangle here, well, we know that tan theta is opposite over adjacent, but we know the opposite is y, or y, right? And we know that adjacent is x, but we also know y is sine theta and x is cos theta. Well, there we are then. So the tan of the angle, tan theta, is going to be equal to sine theta over cos theta. And this is true for all values of theta again, because it doesn't matter where I put my point, it will always be true. So it'd be an identity. But there we are. So we've proven them both here. Okay. So yeah, so we can prove certain particular identities by also considering this sort of constructing a unit circle, and obviously consider get a triangle with the angle it makes with the x-axis in this case. And these two identities have not come out of nowhere. I've not done that for no reason. We will be working with these identities a lot throughout the course in trigonometry. Later on in the chapter we'll be using them. But yeah, this is where it comes from. And I thought a nice little challenge question, I guess, to really reinforce what we've done here. But yeah, so that's working with angles then, in the 4 quadrants. So obviously an angle we can make with the x-axis, as we see in here. We can work out many different angles, and so yeah. So I'll see you next time.